Oh, good morning. I didn't see you all there. Let's go ahead and begin the homework helper for probability 3. The first topic in our ready section is independent and dependent variables. So what this matters about is how one event influences the following event. Now, if one event doesn't influence the next event, they're said to be independent. One does not matter about the other. But if one event relies on the previous event to determine its probability, it's dependent on that action. So, for example, if I were to roll a die here, and I roll a 1, if I were to pick it up and roll this die again, this die doesn't remember what I just rolled. It doesn't care. So when I roll it again, in this case, this symbol represents a 20, all that it cares about is the 1 in 20 chance of any specific number coming up. Now, that would be independent. One roll is independent from the other. But otherwise, when we think about, say, something like a deck of cards, right? When we look at a deck of cards, there are 52 cards. So when I draw a card off the top, now the card that I draw from the rest of the deck, if I don't put this card back in, is dependent on the fact that I pulled the 3 of diamonds out. Now there's only 51 cards in the deck. There's 1 fewer 3, there's 1 fewer diamond, there's 1 fewer red card. So it's impossible for me to pull a 3 of diamonds because it's already pulled out of the deck, but it's also affecting the way every other card works. Now it's no longer a 50-50 chance that I pull out a black card. I have a higher probability of pulling out a black card because it's dependent on the fact that this red card is no longer in it. Okay, so let's go ahead and look at the topics it wants us to look at here. In some of the situations described below, the first event affects the subsequent event, which is dependent, and other events is completely independent of the others. Determine which situations are dependent and which are independent. So all that I'm asking you to do here is to describe whether it's independent or dependent. Okay, so let's go ahead and look at these over. A coin is flipped twice. The first event is the first flip, and the second event is the next flip. When you flip a coin, it doesn't remember or care what it was previously flipped as, so that these are independent flips. A bag of marbles contains 3 blue marbles, 6 red marbles, and 2 yellow marbles. 2 of the marbles are drawn out of the bag. The first event is the first marble taken out. The second event is the second marble taken out. So this is just like the deck of cards example I was doing. Now, since there is 1 fewer marble in the bag, it's going to change the probability of how many marbles are in the bag and the probability of pulling it out because the ratios are different. So this is definitely dependent. Okay, and just go through the rest of these 3 and think about those major factors and whether something is independent or dependent. Okay. Set. We're looking at the addition rule and interpreting Venn diagrams. So Sally was assigned to create a Venn diagram to represent the probability of P, A, or B. And remember, P, A, or B is P, A, and then we use this symbol B for the inclusive OR. Sally first writes P or B equals P of A plus P of B minus P of A and B. But what does this mean? Explain each part. So this is P of A is the probability of A. Probability of A. And then we're going to and the probability of B. Minus the chance of both happening, right? Minus the chance of both happening at each time. Minus the chance of both happening, right? So when we think about our Venn diagram, so this is the probability of A. So we're going to add that to the probability of B. But then for this diagram, Sally takes away this part, and that's why it's not shaded in. But this is incorrect. And it's important to think about why it's incorrect. Why is it incorrect? And the reason it's incorrect is this should be shaded because A and B happening at the same time satisfies the probability of A or B. But what was she thinking? If we're subtracting the probability of A and B, isn't that subtracting this part? Well, kind of. Because look at what's happening here. We need to have at least part of it shaded in. So the A is still true, the B is still true, and they're both happening at the same time. So while this is the correct statement of what is going on, it doesn't mean we completely eliminate this. Now, it's interesting to think, well, since we should be shading all of it, and it's probability of A, which is this, and probability of B, which is this, shouldn't we subtract this? Well, not exactly. We should, because A and B happening together is factored into A, and it's factored into B. So essentially, probability of A plus probability of B would be counting that probability twice. So what we want to do is we want to make sure we don't count it twice, so we take away one of the instances, right? Because you can imagine this is the probability of A, is the purple. Here's the probability of B in the red. So this probability is happening, this probability is happening, but then that middle probability is happening, but the way that we have it designated, it's happening twice. It's happening both purple and it's happening red. But we need to get rid of one of those instances. And so this actually does that by taking away one of those instances. Okay, let's go ahead and turn it around. Okay, whoops, I'm a little too high there. There we go. The Venn diagram to the right shows the data collected at a sandwich shop for the last 6 months with respect to the type of bread people ordered, sourdough or wheat. Sourdough is king. And whether or not they got cheese on their sandwiches. You gotta get cheese. Use the data to create a two-way frequency table and answer the question. Okay, so now we need to create this. Now our margins, our columns and our rows should be the different types that we're looking at. This is a two-way, so one of the ways is sourdough or wheat. So this is sourdough bread, this is wheat, and this will be total. Okay, and then we can use the column, or I'm sorry, we can use the rows to designate cheese or without. So cheese, no cheese, total. Okay. I don't know who doesn't get cheese. Anyway, here we are. So from here we can figure out what's supposed to go in each thing. So our total is going to be 100%, right? By the time we're done, it'll be 100%. Sourdough without cheese is 10%. So sourdough without cheese is 10%. Cool. Sourdough with cheese is 55%. Giving us 65% sourdough. Okay. Without cheese, that's wheat. Without cheese, that is wheat, is 15%. Cheese wheat is 20%, giving us a total of 35%. This gives us 75%. This gives us 25%. Okay, so this is a two-way frequency table where what we're focused on is the total of everything here. Okay, now that we've been able to designate what's what, we'll be able to look at these different probability statements and begin to give the probabilities that are appropriate. All right, let me try to leave this on here. So what is the probability that a randomly selected customer would order sourdough bread, the probability of sourdough bread? So this is sourdough bread with cheese, without cheese, so the total would be 65%. What is the probability that a randomly selected customer would order sourdough bread without cheese? So sourdough and no cheese. So sourdough and no cheese is 10%. What is the probability that a person prefers wheat bread without cheese? Wheat bread without cheese, 15%. And go on like that to figure out all of them. Remember, this symbol is and. This symbol is an inclusive or. Inclusive or. All right. I believe that should be sufficient to get you started on all of this. Let me just double check the back page. Oh, let me do one more on the back page. So the last part is equivalent ratios and proportions. So use the given ratio to set up a proportion and to find the desired value. So if 3 out of 5 students eat school lunch, then how many students would be expected to eat school lunch at a school with 750 students? Okay, so its ratios are always part to whole equals the part to the whole. So in this case, 3 out of 5 is equal to some number out of 750, right? Part whole, 3 out of 5, and we're trying to figure out what that would be with 750. Now, to be able to do this, we just solve for x. So I would multiply both sides by 750, because 750 divided by 750 is 1. 750 times 3 divided by 5 is a large number. Give me a second. 750 times 3. So that would be, first I did 750 divided by 5 to get 150. And then 150 times 3 is 450. So x equals 450. And that's it. Set up your proportions. Part to whole equals part to whole. Okay, let's set up some of these other ones. In a well-developed and carried out survey, it was found that 4 out of 10 students have a pair of sunglasses. How many students would you expect to have a pair of sunglasses out of a group of 45? X out of 45. Okay, multiply by 45 on both sides, simplify, see what we get. Data collected at the local mall indicates that 7 out of 20, and you can see like I'm just seeing this phrase, 7 out of, 4 out of, 3 out of. Those are my clues to create it into a ratio and into a fraction. 7 out of 20 men were wearing hats. Cool. How many would you expect to have been wearing hats if 7,500 men were to be at the mall at a similar day? Boom. Do that, grind it out, simplify it, and go from there. All right. That will do it. I look forward to talking more about these probabilities tomorrow.